In this video, we're going to look at a particular type of line integral. So it is a line integral of a vector field. And this type of line integral comes up when you're thinking about problems in physics having to do with computing work. So if you think back to applications of integration that you probably covered in Calc 2, one of the problems you looked at was calculating the work done by a variable force. Now, if a force is not variable, if it's just a constant, then the work done is very straightforward. You just multiply force by distance. If the force is variable, then you have to construct an integral. And what you saw in Calc 2 is that if you integrate the force function from a to b, that will give you the total work done. But that's assuming that you're going just in a straight line, just in one dimension. And your force function really is just given as a function of one variable, like f of x. So we want to consider the same type of thing, except now we want two things. First, we want the force function to be a vector field. So the force could be, in 2 and 3 dimensions, could be acting in any direction with any magnitude. But also the force could be applied, not just in a straight line, but it could be applied along a curve. And so what this means is that when we're thinking about what this is going to be set up as, we need to really think about what is the amount of the force that's going in the direction of the curve. And you might think back to, this is way back in the semester, when we were first looking at components and projections. And if you think back to there, if you use the dot product with the unit vector, it would basically give you the component in a certain direction. And that's really what we're going to look at here. We're going to look at what is the amount of the force that's in the tangential direction of the curve. Because the only work that gets done is the work that's going in the direction of the curve. We don't want any of the other part of the force to be counted. So this is going to lead us to a line integral with respect to arc length. So the scalar function is going to be a dot product, and it's going to be with respect to arc length, but there's other notations that are used for it, and this particular case comes up so much that you just think of it, it's the line integral of the vector field along this curve. You don't think of it as, well, it's the line integral of the dot product of this with the tangential vector. You just think of it, this is the line integral of a vector field. So we'll go over all the different new notation and ways of computing these that comes up. So let's say that we have a force field, big F, and this is acting along a smooth curve C in this direction. Now, for line integrals of vector fields, the direction, in other words, the orientation, matters. So this is different than the line integral of a scalar that we were looking at before. With the line integral of a scalar field with respect to arc length, the orientation didn't matter. If you went in one direction, you would get the same result as if you went in the other. That's not the case for a vector field. It's going to make a difference which direction we go in. So let's visualize the vectors of this force field lying on this curve. So these are the blue arrows I've given here. So notice they have different directions, they have different magnitudes. Some of them are going pretty much in the same direction that the curve is going. Some are going in an orthogonal direction. Some of them are going in the reverse direction. But what we're interested in is really the component of these along the tangent vector to the curve. So let me, in green, let me kind of draw what those kind of tangent vectors would look like, or what the tangential components would look like. So those are green vectors there that represent the tangential component of the force field along there. And so what we really want to do is chop up this curve into a number of different pieces, and we want to estimate the work done over each piece. Now the work done over each piece is going to be the scalar component of this vector field dotted with this unit tangent. And then it's going to be that integrated with respect to arc length. So it will be a line integral with respect to arc length, but the scalar function is not just going to be some scalar function f. It's a particular scalar function, which is the vector field dotted with the unit tangent vector of the curve. Okay, so let's go ahead and chop this up into a bunch of little pieces. And then we'll look at one of these little pieces and estimate the work done on there. So we're going to form a Riemann sum. Okay, and let's focus in on one little piece. Let's say that piece right there. Now, that piece is going to have a little bit of arc length, and I can take a sample point to evaluate the force field at. And then on that same sample point, I could take the unit tangent of the curve and then dot those two together. That would give me a scalar function. So what I'm going to get is my Riemann sum that's going to approximate the work is going to be like a sum from I equals 1 to n of, so I want to evaluate the force field at this xi star, yi star, zi star. And by the way, everything we're doing here would apply to two dimensions just as easily. You just set the third component equal to 0 and it would line the xy plane. So I'm kind of just going right to 3 dimensions here, but the two-dimensional case is very similar. So I've got the force field evaluated at the sample point, and I need to dot that with the unit tangent vector at that point as well. Now notice, I'm not speaking of a particular parameterization here. That's because the unit tangent, once I have an orientation, the unit tangent vector to a curve is actually independent of parameterization. We talked about this earlier. We were talking about space curves and plane curves. So I don't need to specify a particular parameterization. However, when I go to compute these, I will need a particular parameterization because, as with the scalar fields, we're going to try and convert these into integrals in terms of t that we can actually evaluate. But the definition of this, I just get all this. So I just get the force field dotted with the unit tangent, and I need to integrate that with the little distance. So this is representing, just to be clear, this dot product here is the force. I should say it's the magnitude of the force. Really, it's the signed magnitude. I keep getting more specific and accurate. It's the signed magnitude of the force applied in the direction of c. And so I have to take that force and multiply it by the distance that it's getting applied, and the distance that's getting applied is a little delta s sub I. All right, now, as usual, we're going to let the number of little pieces go to infinity, and the maximum of these length of these pieces. There we go. Sorry about that. So as n goes to infinity and the maximum width of these little arc lengths goes to 0, then we get the exact work done, which is the integral along c of f dotted with t, the unit tangent vector. So these are both really vector fields, right? The unit tangent is a vector field along this curve. So it's f dotted with t ds. So this is a line integral with respect to arc length, right? It's ds. But what we're going to do is we're going to use different notation, and we're going to really write this in terms of a particular parameterization with different notation that's more amenable to how we're actually going to compute these things in practice. In fact, let's look at one of those now. So now let's suppose that we have a particular parameterization of C. Let's say it's R of t is equal to x of t, y of t, z of t, where t runs from A to B. Then what we can do is, let's look at this expression, this f dotted with t. Now, the unit tangent vector, if you remember back to space curves, this is all the way back in chapter 13. this is really defined to be the velocity vector normalized. So it's the velocity vector divided by its length. Okay, and ds, now ds we can think of as, if we multiply and divide by dt, the ds can be replaced by ds by dt, so the derivative of the arc length, dt. So let's write that. ds is equal to ds dt times dt. But we should also remember that the derivative of the arc length function was just the speed. It was just the magnitude of r prime. Okay, so if we put everything together, this is going to tell us that the integral of f dotted with t ds is really equal to the integral from t equals a to b of f dotted with r prime of t normalized by its length, but then times ds, and ds ends up being this, sorry, there should be another dt over here. That ends up being times the speed dt. And lo and behold, the important thing to note here is these end up canceling. So all we're really left with is this f dotted with r prime dt. And that's the way that we really do these in practice. You don't think of it in terms of a line integral with respect to arc length. You think of it as it's a definite integral parameterized by time, where you're dotting the force field with the velocity vector of the curve. And so really we could summarize this by saying that the work done so far, we have two different forms for it. So we have kind of like the definition, which was the integral along C of f dotted with t ds, but that's also equal to this particular integral if we have a parameterization of f. Now here I have to remember that this is implicitly a function of time, because f is a function of x, y, and z, but x, y, and z are each functions of time. So it's really like f of x of t, y of t, z of t, dotted with, I need to move this all over, r prime of t. Now, r prime of t, we'll see later, I'm not going to write it out now, but of course it's x prime of t, y prime of t, z prime of t. So here it's r prime of t dt. So these are the two main forms that we have so far, and we're going to develop, there's other notations. We're going to introduce the idea of integrating with respect to x, y, and z, and then you'll see there's an even nicer, more intuitive way of thinking about this. All right, let's talk about integrating with respect to x, y, or z. So we're returning to scalar functions for just a minute. So let's say we have a scalar field f, and let's say it's a function of three variables here. So we defined the integral of f ds along C. We really said this was the limit as n goes to infinity, and I'll also put just below here as the delta si, the max of these, goes to 0. It was the limit of this Riemann sum of f of xi star, yi star. So the scalar field evaluated at a sample point, and then it was weighted by the arc length. So it was weighted by delta si. Well, what if we didn't want to weight it by the arc length? What if we wanted to just weight it by the change in x. So we could define the integral, the line integral of the scalar field f with respect to x dx. This is going to be exactly the same. So actually, let me just copy this. And all I have to do is change that delta si to a delta xi. So it's just the change in x along any of those one little pieces instead of the change in the arc length s. Okay, and we can get a similar thing for dy and dz. So let's see, I think I have just enough room to copy that. All right, so it's a little cramped, but you can see all of them here. So the point is, why would you want these? So these are kind of different than with respect to arc length. The reason is, I mean, there may be some problems where you're just interested in using it directly, but these are going to be really helpful as another way to write or express the line integral of a vector field. So especially like in the statement of Green's theorem and things like that, the thing that you're integrating is often stated in terms of, integrating dx, dy, or dx and dy and dz, instead of doing it explicitly in terms of, dotting with the r of t. So it just makes it so that it's a way of expressing in component form the line integral of a vector field, but without having to use a particular parameterization. Notice these don't have anything to do with parameterization either. So it's just going to be a convenient way to write things. Now, one thing to be super aware of, as we mentioned before, the integral of a scalar field with respect to arc length is independent of parameterization, but also of direction. Okay, meaning if you go one direction, you're going to get the same thing as if you go the other direction. That is not the case for these. If you change the direction on these, delta x, if you go the other way, it's going to change sign. 5 minus 4 is not the same as 4 minus 5. So these are most definitely not independent of direction, just like the integral of a vector field, we said, was not independent of direction. It depended on the direction. Okay, so before we get to a couple examples, let me just write out some of these different notations here. So these are differential notations for the line integral of a vector field. So what we're going to suppose now is that our vector field is broken down into components. So we can write it as, P, Q, and R, where each of these are functions of 3 variables. And then the integral along C of f dotted with dr. Now, what is this going to mean? Well, this is going to be the integral along C of P, Q, R, and then this dr here, notice it's dr with a little arrow. It's also called, sometimes called ds, so the s with an arrow above it. But this is called the infinitesimal element of displacement, or the infinitesimal displacement element, meaning that it's supposed to represent a little infinitesimally small displacement in the direction of the tangential direction of the curve. So the infinitesimal displacement element can be written as just dx, dy, dz. So it's just the vector that has the little changes in the x, y, and z direction put into a vector. So we're going to dot with that. Now what happens when we do the dot product here? Well, we get the integral along C of p dx, so I'm suppressing the x, y, z here, just p dx plus q dy plus r dz. Now, what's nice about this? Well, what's nice is it breaks down into components the vector field. So if you know the components of the vector field as functions, you can write those out in terms of x, y, and z. But it doesn't depend on the parameterization. I haven't included the t yet. So what you would do now is then you would use, so ... you would use a particular parameterization to convert this into t. So you would be able to convert the p, q, and r into t by substituting in, what x, y, and z are in terms of t. And then also the dx, dy, dz are going to be functions of t as well. So use the parameterization to convert to t. And then you evaluate them just like we've been doing all our t intervals. So this is a very common notation we're going to see a lot. This f.dr and this integral of pdq plus pdx plus qdy plus rdz, or if it's just in two variables, two dimensions, then just pdx plus q dy. PDQ, I keep thinking of PDQ Bach. That's why I keep wanting to say that's PDX. All right, so we should do a couple examples. All right, so we're going to calculate the line integral of the vector fields minus y, x, y squared z. So this is a vector field in 3 dimensions, dotted with dr, where the curve C is this tilted ellipsoid, 4 cosine t, 4 sine t, 4 cosine t. So the best way to think about this is an ellipse that lies on the plane z equals x. And it goes around once in the counterclockwise direction. Now I can show you, let me go to the calcplot 3D. I'll show you kind of what the vector field looks like and also what this ellipsoid looks like. It's not really a tilted ellipsoid. I guess it's a tilted ellipse. I don't know why I put ellipsoid. I should change that. This is ellipse. I'll correct that in the original. But anyway, here's what it looks like. Okay, let me take off the vector field. Okay, so first of all, there's the plane z equals x. Okay, so you can see the plane z equals x, and there's the ellipse that lives in it. All right. So it's that. So I'm going to take away the plane now. And now I'm going to add the vector field. Sorry, I'm just trying to get it there. So I'm going to add the vector field, and what I want you to do is kind of see, do you think the vector field is going the same direction? So we're going around counterclockwise here. Does it seem to be going mostly in the same direction, or mostly against it, or kind of both, or orthogonal to it? If you think it's going mostly in the same direction, then we should expect positive work done. If it's going mostly in the opposite direction, then you should expect negative work, or more if it's more opposite than in the same direction. Or if it's about the same of one or the other, or if most of the vectors are orthogonal, then we can expect that the work would be close to 0. So let me put in the vector field. Okay, it's kind of hard to see, so let me move it around so you can kind of see, and I'll try and, let's look down upon the ellipse. Okay, so there you got a pretty good idea there. So take a look at those arrows. As we go around, do most of the arrows go in the same direction, going counterclockwise, as the ellipse, or against it? So I would say that most of the vectors here go in the same direction. So if you start over here at the right, so if you start on the right here, you notice that first of all the vectors aren't very big in magnitude over there, but they start off a little bit in the opposite direction, but then they quickly turn back to go in the same direction. And then there's a big part up here in the upper left. Notice where they're going pretty much close to the tangential direction. But they're also pretty big magnitudes, so you're going to be picking up quite a bit of work there. Now, they do kind of trail off in magnitude, and then in the bottom left, they are working, I wouldn't say it's in the opposite direction, they're kind of a little bit orthogonal, so there's a little bit of negative work done maybe in the bottom left there. But then in the bottom right, so the pink vectors over there, those are also kind of going in the same direction. So to me, it looks like we've got, in the upper left and the bottom right, two places where we go around this ellipse where the vectors are going largely in the same direction as the curve, and they're pretty big magnitudes, so we're picking up a lot of work there. And then we've got a little bit in the upper right where it's kind of maybe canceling out a little bit. There's a little bit of negative work there. And then in the bottom left, there's maybe a little bit more negative work, but it's not even in the opposite direction. They're kind of between orthogonal and the opposite. So it looks to me, just looking at the picture, if you look at this, that there's more positive work getting done than negative. So I think we should be expecting that there's going to be a positive amount of work done in this. So let's calculate it and see what value we do get. Okay, so what we need to do is calculate dr. So dr is equal to dx, dy, dz. Now, to get these, I have to differentiate the curve. So that's going to be minus 4 sine t, for cosine t, and then another minus 4 sine t dt. A lot of other people will just write dr dt like the r prime, so it's like they're dividing through by dt. I just like to write it as just dr is equal to all this times dt, or you can think of it as each component has a dt and it's almost like I'm factoring out a dt. The reason here is now I can just kind of go directly to f dotted with dr, and I can literally take it just as a dot product. So I'm just going to dot this here. That's going to get dotted with this, including the t, of course. So I'm going to integrate now. T goes from 0 to 2 pi. And so it's going to be minus y times minus 4 sine. Now I have to include what is y. So this is x of t. This is y of t. This is z of t. So minus y dotted with dx is going to be minus 4 sine t. Minus y times dx is going to be minus 4 sine t times minus 4 sine t plus, now I've got x dy. Okay, so x is 4 cosine. dy is also 4 cosine. Plus, and then I've got y squared z. Well, y squared is 16 sine squared. Z is 4 cosine. And then dz is a minus 4 sine. All right. And it's all of this dt. Okay, obviously this is going to be able to be cleaned up quite a bit. Most importantly, these first two terms here. This is 16 cosine squared t. This is 16 sine squared of t. Remember, there's a minus there. So those two together are going to make just 16 sine squared plus cosine squared, and then we've got a 16, 4, and minus 4. So those are going to all together make a minus 64 sine cubed. So that's going to be cubed, sine cubed cosine. Okay, so let's write that down. 16 minus 64 sine cubed cosine dt. Okay, so 16 integrates to 16t. And then the sine cubed, so there's a little u substitution here. If u is equal to sine, then du would be cosine t dt. So I'm not going to write this out, but it's just a straightforward u substitution. Just keep it in mind here. So this is like going to be minus 64u cubed. So it's going to be minus 64 sine to the fourth over 4. And of course that's going to also cancel to 16, but as we're going to see, it's not really going to matter because we're integrating from 0 to 2 pi, and sine is 2 pi periodic. So, so the bottom limit at 0, that's not going to contribute at all. And in fact, the second term is not going to contribute because we're evaluating sine at 2 pi. So that doesn't contribute. So really we just get 16 times 2 pi. And we see that, yes, this does have positive work done. And the work done is 32 pi. Now, one thing I want to point out. Notice 32 pi is not equal to 0. Okay, now that's trivial to note, but why would I be pointing that out? Well, remember, we were going around a simple closed curve, it's called, right? So we were really going around an ellipse, let's say like this. Okay, so we're going around this way. Just all the way around once. And we saw that we got 32 pi. So if we call this, say, c, we saw that the integral of f dot dr here was equal to 32 pi. Now, what I'm going to do is, let's say that by the time I got over to pi, let's say this was at t equals pi, why don't I split this up? And so actually c1 is going to be from 0 to pi, and then let's say c2 is from from pi to 2 pi. What this means is that if, let's compare two integrals. So let's compare the integral of f dot dr along c1, and we'll compare this to the integral along minus c2. So what does minus mean? Minus means you're going in the opposite direction. Okay, so whenever you see minus a curve, that's what that means. It means change the orientation. Okay, so if we're comparing these two, what if these two were equal? Well, let's see. If the integral along c1 was equal to the integral along minus c2. So first of all, notice these are both integrals that go. Whoops. These are both integrals that go from one point to the same point. I mean, they go from the same initial point to the same terminal point. Right? C1 is the green here, and then C2 just goes minus C2 goes the opposite direction, but it ends up in the same place. So if these two were equal, then that would mean if I add, or if I subtract the integral of minus c2, that's the same as adding the integral of c2. That would mean the integral of c1 plus c2, which would be the integral of c, that would have to equal 0, which it doesn't, because it's 32 pi. So what that means is we can conclude that the integral, when I go along c1, cannot be the same as if I go along c2. So the integral of f dot dr along c1 is not equal to the integral of f dot dr along c2. And that shows that this force field here, this minus yx y squared z, is not what we would call independent of path. It depends on the path. We got two different line integrals depending on which path we took. So we would say f is not independent of path. So that might raise the question with you, well, when is one of these line integrals of a vector field going to be independent of path? That turns out to be a really important question, and we'll get a more complete answer to that later when we talk about conservative vector fields versus fields that are not conservative. So let's look at one more. This is a force field in 2 dimensions, and we're going to contrast this to the previous one. The previous one we saw that because we got a positive work done around a simple closed curve, that force field was not independent of path. But here we're going to look at three different line integrals here from the same point to the same point. So the same starting point, the same ending point. 3 different ways to get there, and we're going to see that we're going to get the same answer, all different ways. Now, does that prove that it's independent of path? Well, no, of course not, because there's an infinite number of ways that you can get from one point to another. But it does suggest that maybe it is, and we may even want to bet money that it is. But let's go ahead and calculate. So we're going from the point 1, 0. Okay, so these are very straightforward curves here. We're just going from the point 1, 0 to 0, 1. The first one, I'll do it in blue. So this is the quarter circle portion of the unit circle. And the straight line segment, I'll do that in green. And then I'll do the last one, say, in red. Now we're going to go along the x-axis, and then along the y-axis. We're going to the left, straight over to the left, and then straight up. Okay, so let's look at each of these in turn. So for number 1, the parameterization here, we can use r of t is equal to cosine t sine t from 0 up to pi over 2. Here, dr is going to be minus sine t cosine t dt. And f, since it's y minus x, so y minus x is going to be sine minus cosine. So sine minus cosine, and then x, which is just cosine. Okay, so we're integrating f dr, f dot dr from 0 to pi over 2. So let's see what we get. We've got a sine minus cosine times a minus sine. And then we have to add to that cosine times cosine, and it's all of this dt. Okay, so let's see. We're going to get... So we've got a cosine squared minus sine squared. There's a minus sine squared. Cosine squared minus sine squared is cosine of 2t. And then there's a plus sine cosine. That's that. And that's sine of 2t over 2. Okay, so just a couple trig identities there that we're using. So this is going to integrate to sine of 2t over 2 plus, well, actually it's going to be minus cosine 2t over 4, and this is between 0 and 2 pi. Sorry, between 0 and pi over 2. And so this first term, the sine 2t, when we evaluate at pi over 2 or 0, that's always going to be a multiple of, integer multiple of pi, right? It's going to be sine pi or sine 0. So that's not going to contribute anything. So really we've just got the second term. And so it's going to be 1/4, and I'm just going to switch the order here. So it's 1/4 cosine of 0 minus cosine of pi. Cosine of 0 is 1, cosine of pi is minus 1, so this is 1/4, 2. So we get 1/2. Okay, let's look at the straight line green path. So in this case, so r of t is going to be, so it's 1 minus t times 1, 0, t times 0, 1. So that's going to give us a 1 minus t, comma, t. dr is very straightforward here. It's just minus 1, 1 dt. And our force field, okay, so let's see, it was y minus x. So y minus x here is going to be t minus a 1 minus t. So that's going to be 2t minus 1. And then x, which is going to be 1 minus t. All right, so that means the integral is going to be from 0 to 1. So we have to dot f dot dr. Okay, so that's going to be the 2t minus 1 gets hit with a minus 1. So that's 1 minus 2t. And then plus 1 minus t. So that's the integral from 0 to 1 of 2 minus 3t. So 2t minus 3t squared over 2 from 0 to 1. So that's 2 minus 3 halves, also 1 half. So again, the same 1 half that we got taking the first path. Now for the third one, let's not set anything up. Let's just go back and look up here. So for the third one, along this first piece here, notice y is identically 0. It's 0 everywhere there, which means dy is going to be 0. Okay, so y is equal to 0 and y is not changing. Along the second piece here, x is equal to 0 and dx is equal to 0 because x is not changing. So if we go and we look at our integral back up here, so if we're integrating f dot dr, so f dot dr is equal to the integral of y minus x dx plus x dy. Now, along the second piece, let's look at the second piece here, the one going straight up the y-axis. X and dx are both 0. So if we go back here, since x is 0, the second term here will go away. And since dx is going to be 0, the first term will go away. That means that going up the y-axis, this entire piece contributes nothing. We're going to be integrating 0. Really, all we have to do is just integrate along the first one where y is equal to 0 and dy is equal to 0. So going back here, that means we get, if y is 0, we're integrating minus x dx, and then dy is 0, so the second term also goes away. So we're just integrating minus x dx. Now, think about it as integrating x. What is x varying between? As we go from the point 1, 0 to the origin, x is actually starting off at 1 and decreasing to 0, which means we're setting this up. We want to set it up just in terms of x. I mean, we could use t for parameterization, but we can just do x, and x goes from 1 up to 0. So we're integrating minus x dx from 1 to 0, which would be the same as integrating x dx from 0 to 1, which would give us x squared over 2 from 0 to 1. And again, we get the same 1 half. So in all three cases, the blue, the green, the red, we saw that we got 1 half. Now that does not, again, show that this field here is independent of path, but it turns out that this one is. So no matter what path we had chosen, not just these three, but any path starting at 1, 0, ending up at 0, 1, we would be guaranteed to get a half. That's what's called a conservative vector field, and it's something we're going to talk about a lot later.